Hey everyone, hope you're all doing well. In a previous video I showed you how I remade my router tabletop and a new insert plate for the lift mechanism. And in that video I briefly showed you how the lift mechanism functions and how it was built. It basically works on a crank handle system, whereby turning the crank handle clockwise, it moves the router up, or anti-clockwise, it takes the router down, and that's connected onto a threaded rod that moves the entire system up and down. So in this video I'm going to improve on this system by building a control panel with some electronics. So from that control panel we'll be able to move the router up or down with the push of a button, and also set the router to the desired height directly from the control panel with an accuracy of 0.1 millimeters. So let me go ahead and remove the router lift, and I'll show you how the router lift was built and how it functions. Okay, so I have my router lift now out of the table. Let me quickly show you how I built it and how it functions. It's basically a square box made from plywood that houses the router. Attached to the housing we've got 8 linear block bearings, 4 on each side. The linear block bearings slide up and down on 4 chrome linear rods, keeping the router centered during its up and down movement. And the improvement I want to make to this system, as I mentioned earlier, is I want to make the lift mechanism controllable through the electronics control panel. To do that, I will be removing the threaded rod, doing away with the crank handle system, and replace that with a lead screw. The lead screw has got a bigger pitch in terms of the threads. Then the lead screw will be attached onto a stepper motor, and the stepper motor will be controlled through the control panel, giving us the up and down motion and being able to set it at the exact distance that we need. So the stepper motor is mounted onto the router lift and it's connected to the system via the lead screw. The lead screw works much better than a threaded rod since the pitch of the thread is higher and it makes for a smooth and easy rotation of the nut. So the idea to motorize the lift system is not mine. I've seen it on JSK KOUBOU's channel where he built a similar router lift and electronic control with a stepper motor, and since my router lift is built on the same principle, I thought it would be a great idea to improve and upgrade my router lift. I'll go ahead and link his video in the description below. So I purchased the plans from his website, and this includes the router lift plan, the schematics, as well as the Arduino sketch. But I had to make a few changes to his code since I'm using a nano controller and an LCD screen with the I2C module. The wiring is much easier and cleaner when using this type of module. In my sketch I changed the pins for the inputs or the buttons and added the code for the LCD with the I2C module. So once the router lift is built and connected to the controller, I would need to do calibration of the steps per minute within the code. This will give us accurate movement with my stepper motor and the driver combination. Okay, so let's go ahead and build a controller. I have a couple of components that we will be using, starting with the LCD screen. This is the screen with the I2C module at the back. It makes wiring easier as it only uses 4 pins, and it has a potentiometer at the back for adjusting the brightness of the screen. For the control buttons, I'm using a proto board like this. It's pre-drilled with the soldering at the back, so the push buttons can just be pushed into the board in any arrangement that you would like, and then we'll do the soldering at the back for the pins. I'm going to use a breakout board with the microcontroller, in this case a nano. The breakout board is labeled with all the pins and it has screw terminals for easier connections. And to make those connections, I'm just going to use some jumper wires. Let's go ahead and do the button arrangement, and then we can start soldering and connecting onto the microcontroller. So now I've done all the soldering on the back of the proto board. As you can see, all the ground pins of each button, they are looped and connected onto the ground of the Arduino, and each button has a pinout connected onto the Arduino breakout board as well. This goes according to the mapping in the Arduino sketch. I also have the wiring for the LCD screen that I will attach now, and I've attached the power module. This is a step down from 12 to 5 volt powering the Arduino. Okay, so the step-down module is optional to power the Arduino. You can always do it via the USB. So the wiring is now complete. I'm now ready to add it into the box. I designed and 3D printed a control box with a lid to house all the electronic components. I'm also adding leads for the stepper driver that will connect onto the pull and the direction, as well as the enable pin. Okay, so with all the components and the wiring now done into the case, I have the LCD screen connected onto the breakout board. I have the proto board with the pins and the buttons connected onto the breakout board, as well as the step down from 12 to 5 that will power the LCD screen. So we can now go ahead and power up and see if we get power on the screen as well as the Arduino. Okay, so everything is powered up and it seems to be okay. We can now go ahead and connect the stepper driver onto the stepper motor and see if we have motion in the router lift. For accuracy and calibration, we need to set the correct steps per minute value in the sketch. To do that, I will use an online calculator from MakerStore. In the calculator, I add the current steps per minute value taken from the sketch, then set the machine to move a set distance, in this case 10 millimeters, and press the move button. When the move is done, I will measure the actual travel distance and input that value into the calculator. We will then get a new adjusted steps per minute value, and this value will be pasted into the sketch and uploaded to the Nano. Okay, so the router lift is now back into the table. Everything is connected and powered. Let's go ahead and test. We'll move the router up or down We can move it any distance we like. We can also set a 0, and then we can set a distance for the machine to travel. In this case, 20 millimeters, 20 millimeters up, 20 millimeters down. We can also move the machine in increments of 1 millimeter or 0.1 millimeter in any direction. We also have a set 0 function where we can set the bit to be level with the router tabletop. To do that, I'm going to use a mock-up copper probe like this, and as soon as the router bit touches the copper probe, it will be set to 0. So we'll go into calibration menu, enter, and now it's set to 0. We can do that again. And set to 0.